All right, 5.3. Your goal today is equation of a tangent line and then learning some definitions. And the two definitions you want to hammer down here are called the differentials. The differentials are dy and dx. And I'm going to show you where they come from. And you've seen dy over dx is derivative notation that we never use because we always use the prime notation. But we want to separate them and see where they come from. So the graph will be very helpful. So let's just say we've got a quadratic function. And we'll just call its equation f of x. And we've been using calculus to find the equation for the tangent line at a particular x value. So when we give you an x, you find the point on the function. And then you know tangent line, that's the only point that they have in common. So they share that single point. And then every other place, there's separation between the equation and the tangent line. And the farther we go out, the bigger the separation can be. So, and we'll call the equation for the tangent line just y. Yes, it's a function, but I want them to be different. So I'm going to call this one f of x and this one y. Now, if I pick a second point on the tangent line, so that's my second point. So if I call the first x value an A, I'll call the second x value a B value. So alphabetical order. The distance over and then the distance up between the 2 points, your differential dx is this distance over. That's dx. And your differential of y is the vertical distance between the points. How far apart are they according to the y-axis? That's your differential of y. So that's by definition what they are. We are going to find an equation to get dy. So first of all, your dx is equivalent to your change in x values. And I don't know if chemistry uses this notation, but the triangle x means change in x. That's your b value minus your a value. So your differential of x is just the change in x values, which is just subtract your x values. Okay. The change in y, which we're going to call delta y, we've got two change in y's. We've got delta y and then we're going to have dy. Delta y is the change in y values but on the original function. So at our starting value, the y values are the same for both the original function and the tangent line. But once I go to my second x value, you can see the tangent line has a y value. But in this case, on the function, its y value is higher up. So delta y is the change in y values on the original function. So it would be f of b minus f of a. So it's the distance between these two y values we're going to call delta y, change in y. Now the differential of y you can see is just the difference in y values on the tangent line. So the dy is the tangent line's y value at B minus the y value at A. So remember, y is the tangent line. Now, if with calculus, though, we can get this same result. Remember, dy is our derivative stuff. If we take the derivative of x and multiply it by the dx, that will also give us the dy value. And I'm going to show you that these two come out the same. So there's two ways to get dy. We can just look at the tangent line, but that means we'd have to have the tangent line, or we can use the original function and come up with that same value, which is going to be quicker. All right, and then the last thing they talk about in here is that what's called the error is the difference in these second y values. Remember, at the first x value, the y values are identical, so there's no error. But as soon as I move away from that, now my y values have separation. So at this x value of b, we've got two different y values. This distance is called the error. So that would be the function at b minus the tangent line at b. So you're going to be subtracting the two different y values. That's error. Okay, so now that we have all of the definitions, this little chunk is what's going to guide you through the whole homework section, so keep that handy. Oh, it took me a whole page. I am going to start a new page. So number 1. For f of x equals 11 minus x cubed, find equation of linear function, equation of a line, that best fits at x equals 2. I haven't figured out why they're not just calling this the tangent line at 2, but that's what it is. So you want the equation for the tangent line at x equals 2. All right, and I want you to identify delta x, dx, dy, and delta y, and the error at x equals 1.9. So we're going to be at 2 tangent line, so everything will have the same y value. Then we're going to move away to 1.9. Now there's going to be separation in the y values. So let's make the graph. And I don't have my calculator here, but I do have a sketch of this. So 2 is about here. So we want to find the equation for the tangent line right here. So we are going to need to know this y value over here. So when x is 2, if I put 2 in here, 11 minus 2 cubed, let's see, 2, 8. 11 minus 8 is 3. So this is my starting x value is 2, so I'll call that my a value. Let's work on the tangent line. So that's the first thing you're going to do, is find the equation of the linear function tangent line. So first step for the tangent line obviously, is to find the slope. And slope is the derivative at 2. So f prime at 2. So the first thing we'll do is derivative equation. So derivative of 11 is 0. Derivative here is going to be negative 3x squared. Now we'll plug the 2 in. That will give us negative 12. So we've got a negative 12 slope, and that makes sense because our tangent line is going to be downhill. I can sketch it in right now real quick. Pretty steep. So we'll pretend that actually touched. And after that, we got to find the b. The b meaning where it's going to cross the y-axis at. Looks like it's going to be up pretty high. So we're going to go into y equals mx plus b. We know the m is negative 12, and we've got an ordered pair on our line. The tangent line shares this 2, 3 point. So we know y is 3. Tangent, or the slope's always negative 12. The x is 2. That's going to give us negative 24, so we're going to add 24 over. So we got 27 equals b. So our tangent line equation is y equals negative 12x plus 27. So, okay. Now it says we're going to move to 1.9, so that's going to be really close. Well, I'm going to exaggerate it a little bit. 1.9, that's our b value. So now when we go straight up, the original function is going to have a y value. And then the tangent line is going to have a different y value. So we can find these two y values because we're going to need them. So plugging 1.9 into the original function, which was up here. So f of 1.9 where do I have that at? F of 1.9, 4.141. 1. And then y, which is the tangent line at 1.9. Plugging that into the negative 12 times the 1.9 plus 27. I'm getting a 4.2. So this first one is 4.141, and then we got a 4.2. All right, so that's everything we need. So questions were change in x. Well, change in x is just the difference in our x values. And I believe it has to go b minus a. The new one minus the original one. So b minus a is 1.9 minus 2. That's giving us a negative 0.1. And that makes sense because when we moved to our new x value, we went backwards, and that's indicated by the negative here. If we move forward, our change in x is going to be positive because we're getting bigger. All right, so then dx, well, dx is still the change, it's equivalent to it. Dx and delta x will always be the same value. So dx delta x, always the same. Okay, I asked for the dy and the delta y and then the error. So let's go, it doesn't matter, I'll go delta y next. And if you look at the definitions, where did I put you at? delta y is on the original function. I have to subtract the two y values. So that would be that cubic. So I want the f of 1.9 minus the f of 2. And we have these up here already. The f of 1.9 was the 4.141. And then the f of 2 was 3. And then get a difference there. Where am I at? Delta y. 1.141. Oh, 1. Okay, and now the differential of y. And we're going to do this one two ways. So we're going to do it with the original definition was that's the change in y values on the tangent line. The change in y values on the tangent line, 2 points. So we want the y value at B minus the y value at A. So at B, which is the 1.9, the tangent line had a y value of 4.2. The y value at the original was 3. So the differential of y is coming out 1.2. That's easy to do if you have the tangent line. Now look at all the work it took us to get the tangent line. If we don't have the tangent line and we want the differential, we can use calculus. And by definition, you take the derivative of x multiplied by the differential of x. So I'm going to write that down again. So the first thing we will do is do the derivative of the original f of x. So derivative is 0, and then we would have a negative 3x squared times the differential of x. And now we want that differential when x is 2. So we'll put a 2 in for the x. But the differential of x is a negative 0.1. So that builds in that moving to that new point and working all this out with some magic. So if we multiply out, we're going to have 4 times negative 3 is negative 12 times that negative 0.1, positive 1.2. So they do come out the same. So not having a tangent line, we can use the calculus to get it. And you're going to see a connection here in a little bit to differentials and getting back to something special. All right, that was a long one. Number 2. Oh, I forgot the error. Holy crap, there's still one more part. Error. Error, if you look at the graph, how far apart the two different y values are at the second point. So we want the, it's the function y value minus the tangent line y value. So function is 4.141 and tangent is 4.2. So we have a negative error, negative 0.059. Okay, that's everything. And I will be kind to you and have all of these written on the board for your test. Merry Christmas. So, you don't have to memorize all of that. Okay, so with that being said, I've got a spot on this paper. That's okay. We'll work right through that. Next one. Number 2. Number 2. Can you find an equation for the differential dy for f of x equals 1/3 x to the 5th. Well, we're just going to use that calculus because we don't have the second point. We're going to be using the fact that the differential dy equals f prime of x times dx. So, all I've got to do for the differential dy, well, let me write down the definition. All we have to do is take the derivative of this and then stick a dx on the end of it. Okay, so we're just doing derivative. So we multiply down, that'll be 5/3 x to the 1 less, and then times dx. That's the differential equation. Done. It's simple. Don't make this challenging. Just by definition, you do the derivative times by dx. So a second one. Let's see if we have y equals 4 sine 2x plus 7x squared, and we want the differential dy. We don't do anything different than we did here. Dy equals derivative of this, so that will be 4 cosine 2x times by the derivative of the angle plus derivative here is 14x. And I've got to take the whole derivative and times by dx. Well, because there were two parts to the derivative, you have to have parentheses with a dx on the end. And the only thing I should do is simplify here. So I will have 8 cosine 2x plus 14x all times dx. Okay. And then the last thing we're going to do is go backwards. So, remember our notation for, well, maybe you don't remember because I didn't make you write it down, but another notation for f prime of x was dy over dx. These are equivalent notations. So, keep that in mind as we do the next one. So you need to find an equation for the antiderivative equation y. Alright, and here's how we go about it. If we have the differential dy equals 15x squared dx, what we can do is bring this dx to the other side by dividing, just regular straight up algebra. Divide by dx, divide by dx. Now I've got dy over dx. Remember, that's just y prime. So what we have is y prime equals 15x squared, and our goal is to get to y. So to get to y, I've got to do the antiderivative. And this is what we did yesterday. So that rule says you know it starts with one higher on the exponent. And now you check to see if you need a multiplier here. If I do derivative, 3x squared. Well, I don't want a 3, I want a 15. So that tells you need a 5 here. That will give me the 15x squared. And you know we need a plus C for the constant of, oh, you don't know that term yet. Okay, plus C. And we'll do one more. So all we're doing is connecting differentials to antiderivative. So when you're given a differential, 5x squared minus 2x plus 1 all times dx, we know if we divide both sides by dx, we'll have the derivative equation. So dividing by dx, that makes this y prime. That's gone. We have these three terms. And the goal is to get to y. So we're going backwards. So what has this as its derivative? Well, you know it started with an x cubed. So if I left it, it would be 3x squared, but I want a 5. So you got to figure out what this has to be. Well, let's just call it n for now. So 3 times my number that's sitting here has to equal 5. So 3 times my number I need here has to equal 5. Well, divide by 3, it's got to be 5/3. And you can see the 3's cancel. What has 2x as its derivative? Well, you know it started with an x squared. Multiply down to x to the first. Oh, that's exactly what I wanted, so I don't need anything else there. What has 1 as its derivative? I need something to get me to 1. That something is just x. X to the first. Derivative of x goes to 1. Then r plus c. And there it is. So we're taking differential equation and coming and doing an antiderivative to get back to the original. All right.